right? Okay, let me just go back and review. So what we are talking about something called a time reversible Markov chain. And one of the easiest way, or one of the simplest way to think about a time reversible Markov chain means that if you are able to move in one direction, like from state 0 to state 1, then to state 2 at a particular time, then it means that you are able to move from 2 to 1 and then from 1 to 0 like that. That's a simple way of thinking about it. And so we will be assuming that our initial Markov chain, it is ergodic, right? So we have this theorem that says that if that holds, that condition holds, then pi j is the limit as n tends to infinity of pi j to the n, right? So we know that this, this definition from previous class. So these pi j's are what we call the limiting probabilities, and we know that the sum of these pi j's would be equal to 1, right? Because it's just a probability distribution. All right, so this is the original Markov chain. And in the original Markov chain, we are moving in this direction, all right? We are moving from state n plus 2 to n minus 1 to state n minus 1, then from state n minus 1 to xn. But we can trace the Markov chain backwards. So when we can also do the reverse, meaning that we can start at this point and go in this direction, then we refer to it as a time reversible Markov chain. So we are assuming that this is a Markov chain, and we're also assuming that this here is a Markov chain, right? So those two are Markov chains. So the basic idea is that if you could move forward, you can move backwards as well. That's the basic intuition behind the process. Okay, so let's talk about yeah, and moving back to the other, in the other way. So if the fly was at this point here, and went to this point here, B, then it can also move from B back to A, right? So we have that. All right. Okay, so let's look at the transition probabilities that we have here. So this Qij, this is the transition probabilities for the, let's call it the reverse Markov chain. Right, so that means that it's going the other way, right? So the probability of, so this Qij is the probability of moving from state I to state J, right? So you're moving from state I to state J when you are in what? State m plus 1, so you're moving from m plus 1 to m, right? So this is just a conditional probability here. So what we could do, we could break this thing up. So this is just the probability what? Of A given B. So this here is the probability of A intersect B over the probability of B, right? So this is, so this part here is like event A. This here is like event A. This part across here is equivalent to say event B, all right? And we want to get the conditional distribution of A given B. Well, we're just using this formula that I have on the across on the right hand side here. Uh-huh. Yeah, yes. You're right. So okay, I'll come to that. You wanted to find out if P1 JI is equal to pi I. Well, if the stationary distribution holds, then right. So if it's ergodic, so let's go through this and make sure. So this part across here, we have the intersection of this and this happening. But across here, we could decompose this and is, when you see a comma in statistics in prob, a comma here, this means and, right? So this is event A, this is event B, right? So let's look at the numerator alone. So how can you break up an intersection if you have something like this? How can you break this thing up? Well, you could break it up like this, right? Right? You could break it up like this. So you could break it up into a conditional probability and into a marginal probability. This is called a marginal probability because it only has A here alone. And this one across here has a given that, right? So this one here is a conditional probability, right? So this is why we call it marginal and conditional. So what I will do is I will try to look at the intersection that I have here and try to break it up into two pieces, into a marginal probability and into a conditional probability, right? So that's all I'm going to do. So I'm going to treat this here. So let me just erase some of these things here. Right. So I'm going to treat this thing here, this part here in the numerator, right? So that's the probability of xm equal to j and xm plus 1 equal to I. And this here is the probability that you take this event here as A, take this part here as B. So what I'm going to write down is probability of A times the probability of B given A. Right? So that's what I'm going to break it up into two pieces. So this part here is the probability of xm equal to j multiplied by the probability that xm plus 1 equal to I given, right, because this is B, given A, right? So given xm equal to j, right? So we have the situation here taking place, right? Now, what did we say about the initial matrix? We said that it was stationary, right? So that means that I can replace this first term here with pi j, right? So this term here is equal to pi j since the Markov chain is stationary, right? So by the ergodic theorem, we have that they have been pi j. What about this part across here? Well, this here is just moving from state J to state I in how many steps? Yeah, in one step, right? So we just move in one step. So if it's one step, then if you picture the transition matrix, right? The probability matrix, it will look like this. So this is m plus m. You move in from state what? J j to I, right? So that probability here would be pji, right? So this number here is simply from the original Markov chain transition matrix that we have with the p's, with the probabilities. So this here is just pji, right? So we have the numerator at the top, and the denominator says that the probability that p m plus 1 equal to I is simply pi I, right? Because again, the Markov chain is what? It's stationary, right? So far, what do we have? So far, we have is this. If what? Not all the time. Yeah, so yeah, not all the time. Yeah. So you have to be careful with what's with this one. So this one says that Qij now is equal to pi j plus pji over pi I. So you could cross multiply and you get like pi I q ij is equal to pi j times pji. So we have a relationship between the new or the reverse transition matrix and the initial one that we had, right? So there's some one-to-one relationship that exists. Right, so time reversible now, a Markov chain. A Markov chain is time reversible if the Qij is equal to Pij. So now we're making another assumption that if it's time reversible, then the probability of moving from I to j, either going forward or going backwards, is the same. So that means that Qij is equal to Pij is equivalent to saying this, right? So remember, if we make the assumption that Qij is equal to Pij, then all we are doing is that we are just transforming this to Pij. So we have this relationship in a time reversible Markov chain. Which part? Yeah, over here. Right. So in a time reversible Markov chain, this is what happens. The new transition matrix that you have, the Qij's is equal to the Pij's. And we've already found a relationship up there with Q and Pij's. So if they are equal, I can replace this Qij with Pij, and that's it. Right. So I just wanted to be aware that we have some relationship that exists between, and we have Markov chains that are what we will call time reversible. But in today's class, what I want to do, I want to go in a little bit, and you could read a little bit more about it and look at these examples. For example, a random walk is one of those, which is time reversible, right? So you can go in one direction, but you could have a Markov chain that goes in the other direction as well. So I believe I have two examples here. You could omit this one. This one is with respect to graph theory, so omit this one. But the first example might be useful. Okay. So in today's class, what I want to do, in addition to that, I want to just review queuing theory. I'm not too sure how many of you did you all meet queuing theory like in the undergraduate courses anyway? Okay, so you're aware that it exists, right? You did anything? Okay, so we didn't do anything at the undergraduate level. No problem. All right, so yeah, the only example is, well, the simple example about queuing theory is the one that we always talk about, the traffic light and the waiting time and things like that, right? Elevators, your banking system, anywhere you go and you have to line up or take a ticket and sit down. You're in a line, right? So, and we have various definitions and various things that we could think about. So if you have one person here and this is your server, the server is a person giving you service, right? And you have a single line. Am I recording? Oh, right. Oh, okay. Sorry. Right, right. Okay, so okay, so many of you or most of you would not have met it. So there are different types of queues that we meet in the real world. The first one might be something like this. You go to the bank or you go to a system and you have to join a line. So there'll be one person in service here, and then you'll have a few people in the line, and you just join at this point here, right? So this one here is a single server service, right? Only one server. But you could go if you have been to the airport sometimes, especially when they are loading say passengers into the plane, they will always ask if anybody want to come and give up their luggage so that they could go with the not in the overhead compartment, but with the rest of the stuff. So what you might have here, you might have 3 people at the counter, but everybody will have to join a line. There will be a single line, right? And you join, say, here. And what you have is you have a multi-server system. So in this case, you have multi-server. So these 2 examples that we have of queues here is basically a single line. But that's not true all the time, right? So that's not true all the time. And we can have a lot of restrictions on the lines as well. So we could have a lot of restrictions on the line. For example, suppose I have 2 lines now, right? So I have 2 lines like this, and I have, 2 queues like this. But if I am in this line here, so this is my first server and this is my second server. So like if you go Pennywise or something like that and you join, they have about 8 cashiers up front, and each cashier has their own line, right? So in a case like that, what happens is that you just join one of the lines. Normally it's the shortest one, and things like that, right? So in this case, you have 2 queues, and you have 2 servers, and people can keep on coming here, right? As the day progresses. Another queue might be, you go in a garage, a mechanic garage, and you have one mechanic, and but his garage only has place for, say, 4 cars. So 1 car comes in, second car comes in, third car comes in, fourth car comes in. He doesn't have place to store any more cars. So if a 5th customer coming with a car, the 5th customer has to leave, right? So now we put a restriction on the size of the queue. right? So here we have a restriction on the size of the, right? So we have this restriction on the size. So there are tons of other examples that you could think about in the real world that exist that that fall into various forms. So now we'll start talking about the different types of cues. And we're going to be a little bit more specific now when we talk about these things. So we're going to talk about arrival time and service time. So the arrival rate, we'll think about it as following some distribution, and the distribution that we normally use is the Poisson distribution, right? So normally it's the Poisson distribution with parameter lambda, right? And the service time that we normally take, or I should say the arrival rates, or arrivals, I should say, are normally, say, Poisson lambda. And the service time, the amount of time that you spend in front of a server, is normally exponential distribution with parameter mu, right? Now, if you are in the field and you are actually conducting some sort of experiment, you cannot assume that the data came from a Poisson or the data came from an exponential. So what we'll do is we'll normally make an assumption. We'll normally take some empirical data, see what it looks like, and then we will use some appropriate distribution. So not all the time the Poisson distribution is appropriate or the exponential, but it so happens that most of the times that it works, and it works well. All right. So we're going to assume that the arrivals and service times follow some distribution. If they don't follow some distribution, then we're in trouble, right? Then we don't have any statistics to deal with, right? So the first type that we are going to look at in the course is a single server queuing system. So a single server queuing system. Single server queuing system simply means you have one server and one line, right? And the second type that we're going to look at is the multiple server queuing system. And so those are the two, right? So we have the single system, the single server queuing system that looks something like this. So one looks like this. You have one person and you have a line here, right? And multiple server, you have more than one server. So this is, and you have some line like this. Maybe this line is kind of long. So this here is the front of the line, and this here is the end of the line. down here, right? And over here you have 3 servers. So we are talking about multiple server system where you have more than 1 servers, and then we have single server where we just have 1. But we have some restrictions built into these things now. So let's look at some other restrictions that we might have. So within the multiple and single server system, we can have a finite queue length. Right, so that means that the U.W.I, yeah. You spell it backwards. Okay, all right. So so here we have some sort of restriction, right? So this is the restriction here. So we restrict the queue length to a fixed value. For example, the number of persons that can be seated in a doctor's office. Right, so you know, if people are coming into a doctor's office, the office is small, right? So this might be how the office is. So you have 1 doctor, this is the doctor here, right? That's the doctor in the corner there, and these are your patients. They come in, but you might only have limited seating, right? So that means the queue length has to be limited, right? And there's still a queue here because as people come in, what they'll do is they'll first go to the receptionist and they'll be placed in line, right? So they will be part of the line. So in this case here, we have a finite length of the queue, right? But we could also have an infinite, right? So we can also have an infinite queue length. Yeah, they leave, yeah. So yeah, so once you don't have any seating for somebody across the doctor's office, if the number of seats for the patients have been all taken up, then whoever comes after will have to leave, right? So now we will talk about an infinite queue length. So here there are no restrictions, right? So here there are no restrictions on the number of persons in the queue, right? So you come, you could just join, and however long this line goes, it goes, right? So nobody is going to throw you out of the line or tell you to go home or anything like that. Right. So the next thing, or the next aspect of queue length is not only the length of the queue, if it could be finite or infinite, but it could also represent if the population is finite or infinite. So we're talking about Q length being finite or infinite, or we're talking about the population being infinite or finite as well. So the population can also be finite or infinite. So an example of an infinite population well, there are some doctors who will never refuse anybody. So wherever they get, whoever they get, so this is your doctor here. Huh? Yeah, the health center. So right. So once you join, you are in the queue, right? So there's no way anybody's going to take you out and throw you off, etc. So the population represents really anybody who could attend. An example of a finite population might look something like this. Let's think about it like this, right? So you have some company and you have one mechanic, right, or a team. So one team, and this team here, they're in charge of fixing machines. But the number of machines that this company has is only 4. So in this case, this server, this here is my server, right? This team, the single server has a population that is finite because only 4 machines that they could look after, right? So in this case here, it's finite. The population is finite. Everybody understand that? Good. Yeah. So in this course and most of the courses that you will experience Q theory with, a lot of the theory have been built up using the Poisson and the exponential distribution. So we'll stick with that notation, right? Huh? Yours, yes? I didn't hear that. About the toothpaste? Yeah. Okay. No. The queue is not continuous, right? The queue is discrete. So that means that it's not like squeeze. Okay, I understand your point that all the toothpaste trying to squeeze through and get outside, and maybe when it's outside the service. But in that system is not like the number of arrivals within a certain number of time and things like that. So in that case, it wouldn't be equivalent to a queue. It would be equivalent to some continuous thing, but I wouldn't call it a queue, right? I wouldn't call it a queue. So most times, the arrival rates is Poisson with rate lambda, let's say per hour, and the service time is exponential with rate, say mu, say per hour, right? Because we are touching our rate mu. and lambda, right? So in this case here, we are going to assume that we have arrival rates will be at rate lambda, and the service time will be exponential with rate mu, right? So people are coming in at the rate lambda, and they are being served with rate mu, right?
So I might be missing something.
If lambda over mu is less than 1, we have infinite queue length. Can I hear? Didn't hear anything.
So you could hear me?
Okay.
All right, I guess not.
Oh, right. No, it could be any, it could be at any time, right? So if you are being served, right, you want to get some average per interval of time. So you normally put it per hour, per day, per week, or something like that. It doesn't have to be yeah, it doesn't have to be per hours. All right, so I'm just using per hour. It could be per minute or per 30 minutes, etc. All right. Okay, so what do we have if lambda over mu is less than 1? So if lambda over mu is less than 1, then it means that we will have what? We will have the rate at which service is taking place is faster than the rate at which people are coming in the queue, right? So that means we could write it down a little bit. So an example, if say lambda is equal to 5 arrivals per hour, and let's say mu is equal to 6 arrivals per hour, then lambda over mu is equal to 5 over 6, which is less than 1, right? So what does this mean? This means that every 10 minutes, a person gets served, right? Because we have what, 6 per hour. So every 10 minutes, a person gets served, and every okay. U is equal to 6, 5 over 6. This is correct, right? Yeah. No, I'm putting the second one. Sorry, I'm putting the second one, and I'll put the first one. So every what? Every 12 minutes, a person what enters, right? Or arrives, right? In the system. So every 10 minutes, a person gets served. So that means the service time is less than the arrival time. The arrival time, yes, sorry. The arrival time is less than service time. The arrival time is 5, the service time is 6. Yeah. Right, so the inter-arrival times or the time at service would be exponential, but the rate of arrivals or the rate of its service is taking place would be at mu. So you could convert it just into arrivals instead of thinking about the exponential. You could think about it in terms of the Poisson rate, the number of people being served in a particular hour, right? What's the rate that they would be served? All right, so let's see. There are some other notation that we need to just clear up before we actually start Q in theory. There are some terms some definitions that we need to look at. There's something called bulking. Right, so let's see what bulking is. So if you have some shop here, right, and they cannot come in. So let's take an example. So we have our mechanic here, and in our mechanic shop or his garage, it could only have 4 cars. So he only has space in his garage for 4 cars. So any new car coming in will automatically be turned away. This is what we call forced bulking. Right? So we have 2 types of bulking. So this is where somebody wants to join the queue. In this case here, if the queue has a maximum length, as in this case, the maximum length is 4, it cannot take any more cars, then any new car coming in must leave. So in other words, we have what we call forced bulking. Now, if you are in some grocery or something like that, and you decide to join the line. So you have a server here, and you decide to join this line, right? But then after looking at your clock or your watch, you say, but wait, it doesn't make sense staying in this line. So now you have moved over to some position here, because you realize that it's taking too long, you exit here. So you have decided to leave the line voluntarily, right? Yeah, right. So this was unforced bulking. So when you read about Q in theory, you'll read about these 2 things. The first one, forced bulking, and the second one is unforced bulking. The next term that we're going to look at is reneging. So this one here is to join the system, and after some time, leave the system. So you join a multi-server system, and after some time in this, you decide, I'm no longer interested, right? So this is, you normally get this in when you talk about multi-server queues. And the third one is the one maybe you all would it's called jockeying, right? And jockeying is simply this. You have you have a multi-server system. So let's say this multi-server system, say, has 3 servers in it. And then you have queues like this. Right? And you are the new person here. This is you. And you decide, you look at the entire system and you say, okay, I'm going to join here because this one is shorter. Then as you progress, you realize that that the first cache is taking a long time. And what happens is that the second cache went down to 1 person. This one here went down to 2 after some time. And then you say, you know what, it doesn't make sense staying with cache 1. I'm moving, I'm switching positions to 2. So this is what we call jockeying, right? So this is when you have a multi-server system. Okay. Maybe you would have heard about this if you have done computer science, some computer science courses. You would have heard about this term, first come, first out. You all heard about that? No, nobody did computer science. Yeah, so reneging is normally when you have a multi-server system. And bulking is normally when you have a single queue. So bulking exists when the size of and not only that, bulking occurs, when the size of the queue matters, right? So you could have, if the size of the queue does not matter, you have unforced bulking, meaning that, you could join the line and decide to jump out of the line at any time. But the example with a mechanic shop is where the mechanic, you have a queue in his garage can only have 4 cars. So bulking really, so it cannot take any more new cars because the size of the queue now is fixed. So because of that now, here, whoever joins, right? Whoever joins has to leave. So the other one is first come, first out. So this is a normal way that we think about a queue, right? The first person who will join the queue is the first person who will get service. Then that person leaves, then the second person gets service who was in the line, etc. That's the normal way. So when you hear the term first in, sorry, when you hear the term first come, first out, this is what we mean. All right, so far what can we say about these queues and things like that? We can have single server queues, we could have multiple server queues, we could have finite queue length, and we can have infinite queue length, right? So today, what we're going to look at is something called a single server infinite queue length model. So this is the one that we're going to look at today. And just some notation, we're going to look at it as M1 infinity infinity model. So this is the notation that we will use to represent this queue. So I need to explain what these M's and these ones are, etc. So the first M tells us the arrival rate. The second M gives us the service rate. This one here is the number of servers that we have. The infinity, the first infinity here is the queue length. And the last infinity that we have here, this last one across here, is the population. Are those slashes or vertical lines? Or those are slashes? So maybe I should put it like this. What? Well, regardless if you use vertical lines or slash, once they are separated, I'll have a good idea of what they are, right? And the arrival rate that we are looking at is Poisson lambda. And the service time that we are looking at is exponential mu. And we are relying on a memoryless property. This last infinity that you're seeing there is whether the population is finite or infinite, all right? So although I didn't write it down here, this refers to the fact if the population is finite or infinite. Right, so the queue where we had, remember I said you can have one mechanic team in a factory, but that team only sees about 4 machines in the factory. So in that case, the population that it could see about, right, that it will look at will be finite. But if you join an ordinary line, then and people joining a line, then that's infinite, right? Everybody okay with this? All right. Now, we're going to rely on the assumptions or the definitions of the Poisson distribution we used the last day, or we went through the last day, in order to come up with something called a steady state distribution, right? For these Qs, right? So we're going to make some assumption that during a very small interval h, only one event takes place. Right, so that means if only one event takes place, that means something could either arrive, somebody could either arrive to this in the system, or somebody could leave the system, right? So one arrival or one service. And this is what I mean. And what I'm going to do now is I'm going to define some notation that is going to speak about the probabilities, right? So what is the probability at steady state? Yeah. We will just, okay, so in the general trend of queuing theory, it's like you have one line, and this is the basic notation. You have one line or one queue length, and you are moving, you are joining, so you have one service, so you have many servers, and you have a line, one line or many lines. So those where you have to leave one and then get to the other one, you could think about it like having two servers, one here and one across here, but then the length of the queue on the second server will depend on the length or on the number of people who have left the first server. So you can think about it, but those two queues now are dependent on each other. It's not like the one like we were talking about Pennywise, where people just join separate queues, where they're more or less independent, right? Okay, so we are assuming that in any interval here, we will have just one, in any small interval, we just have one event. And that one event could either be an arrival or a departure, right? Service. So somebody will join the queue or somebody will leave the system. And the probability that we are at steady state in the system, steady state, think about it as having a stationary distribution, right? At the system means that we could have either 0 persons, we can have 1 person, 2 persons, etc. So what we want to work out now is some probability in general that, we'll have like no persons in the system, 1 person in the system, 2 persons in the system, etc. So these are the probabilities that we would want to work out. So these are probabilities, right? Now, some other things that are important for us when we talk about queuing theory. The first one, I'll just introducing them some notation again. The first one is LS, and this is the expected or the length of the system. So when we talk about the length of the system, it is really the expected number of persons in the system. This includes the person being served. So this is the first term that we need to be aware of, LS, which is the expected number of persons in the system. So an easy way to remember this is this S here represents system, and L is the length, so it's the expected length, right, of the system. Then it will be LQ. LQ is simply the expected number of persons in the queue, right? So the expected number of persons waiting for service. Yeah, the waiting time, yeah, the expected waiting time in the system. And number 4 is the expected waiting time in the queue, WQ, right? So although I didn't use the term expectations in 1, 2, 3, and 4, they are all expected values, all right? So let me just put a note to that. That 1 to 4 are all expected values. What we're going to do now, so we have some terms that we define here, but in order to get these terms, we really have to look at the probabilities, right? So we're going to define some probabilities now. And the probabilities are going to be defined as follows. So the probability that you have 0 persons in the queue is P0. The probability that you have 1 person in the queue is P1. 2 persons is P2, etc. Right? So that means that if you have n persons in the queue, this would be Pn. Yeah, we will develop a function, or we will derive this function for Pn in general, right? For one of the Qs, and then I'll show you how to get LS, and then from LS we could get all the others, LQ, WS, WQ. So you could, so far we could think about this like this, right? So we are here. So this is our input. We have the arrival rate lambda, we have the exponential rate mu, and we have C, which is the number of servers. In this case, C is equal to 1 if we have it. What we do is we do this. We use that information and we go to an intermediate step and we work out what these PIs are, right? So we get functions or expressions for these probabilities, and then we use this now to get our final output. When I say the final output, I mean I can use my probabilities to work out things like LS, LQ, WS, WQ, etc. Right? So this is so this is the step, or this is the overall step that we would look at this from, right? So this is the output, right? So these are my inputs. So the only inputs that you have is the arrival rate, the service time, the number of servers that you have. Convert all that into probabilities, right? And this is the intermediate step. And then we get to the output. The output is where, people would be interested in, what is the expected length of time? How long would I have to spend in this line if I decide to join it? Things like that. All right. So this is what I'm calling my final output. So what we'll do is we will get a general expression for Pn, right? So we're going to get an expression, a general expression for Pn. Pn simply is the probability that there are n persons in the system, right? So let's look at it by means of a diagram. So if we have n persons in the system here, then I could have had n+1 system in the person before, and then I moved over to n. So then I have one person had to do what? Leave, right? When one person leaves, that means that person has been serviced, correct? So one service. Any arrivals? No. So one service and no arrivals. What about now? Can I have n and end up with n? Yeah, I can have that, right? How I can have that? Okay, so I can have one arrive and one get service within that time, right? So one arrival and what? One service. Anything else? Nobody gets served and nobody what? Nobody came in too, right? So 0 arrival. You understand? Yeah. Zero arrival and what? Zero service. Okay, what's the one after n plus one and what I should have after? Yeah, n minus one. Okay, n minus one, to go from n minus one to n, what I should have? Yeah, I should have one arrival and what? And no what? And no service, right? So this diagram here is going to help us in writing these in writing these things down, right? So let's see how. So moving from n plus one to n, we have one person must leave for this number to decrease to n, and nobody should arrive, right? Then from n to n, then I could have one person coming in and one person leaving, and that will give me n. Or I could have 0 person coming in and 0 person leaving, and that's also give me n. And then I could have n minus 1, and to get to n, then I must only have one arrival, no service, right? Okay, so now we'll use that diagram now to write down this formula here and see if this makes sense. So Pn T plus H. So that means the probability that there are n persons, right, at time what T plus H means that there were, let's see, there were n minus 1 persons at time T, and there was the probability of what? One arrival and no service, right? Plus the probability of n plus 1 t times, that means that at time n plus 1, right? At time t, sorry, we have n plus 1 individuals, but to get to n, that means one person must leave. So we have one service. So the probability of one service, I'm writing this, and no arrivals, right? Plus the last one is P and T. That means that in that small interval H, that nobody came in, nobody left, right? So there's a probability of no arrivals and no service, right? Right. So we have a little now I wrote down my answer like this, but is this equivalent to what we have here? Right. Yeah, this one here, right? Right. So we have everything here except this line here. Let me just put this line in orange. Now, who could tell me why I'm not including this inside here? Okay. At the beginning, we said what? In a small interval H, only what? One event could occur. So that means we cannot have one arrival and what? One service in an interval H. So that's 0. That probability is 0. So that's disappeared, right? So that's out of the picture. Exactly. Yep. So so let's rewrite this expression now, this big expression that I have here. This thing here, in terms of probabilities, these probabilities, convert these things to these probabilities here, right? So let's see, Pn t plus h is equal to the probability that you have one arrival is what? It's that will be Pn minus 1t. So I'm looking at the first line, this first line here, multiplied by the probability of one arrival and no service. So one arrival is lambda h, and no service is 1 minus mu h, right? Let's go on to the second line. The second line says plus Pn plus 1t times the probability of one service and no arrivals. So one service would be mu h, and no arrival would be 1 minus lambda h, right? And the last one, should put a plus here, would be Pn minus Pnt. And this one has what? Pn minus 1t means 1 Pnt. That's no arrival, no service, right? So no arrival, no service, no arrival. Let me put this, and no service. Right. So I have all the terms here. Okay, next step, just multiply all those things and simplify. Remember, anything that has OH that is greater than, if OH is any function that is of order OH, we'll say it's 0, right? So if we multiply these things out, I will get this. So I'll put this one here in this color. Pn t plus h is equal to Pn minus 1t multiplied by lambda t, right? So I wouldn't put down this part here because this would be h squared if I multiply that. So that's out, right? So only terms that has h. Sorry, lambda h. I put lambda t, right? Plus the other term now, this line here, I can multiply this by 1, right? But I can't multiply this by this because then that term would be h squared, right? That would be OH, so that will be 0. So now I will have Pn plus 1t times mu h. And the last term now, let's see, I could have this part here, P n t into 1 minus lambda h minus mu h, right? The term in I believe that's it. That's 1 minus mu h minus this plus lambda mu h squared. So the lambda mu h squared is of order h, so it's OH, sorry. So that will be 0, right? So now I have this this term here. I'm just going to put down, write this like this now. PNT. Okay, I can't fit on this line, so I'll put this here like this. So this. Huh? Why I did what? Yeah, I'm going to take the limit. Yeah, yeah. So it's like it's like a derivative, but when this part here, the probability that you get an event, remember, the event is t plus h minus the probability of t. The probability that you get an event in h is almost zero, right? So this part here will disappear. It'll go to zero, and then you'll be left with this part here on the right hand side. So So all I'm doing is I'm just dividing across everything by h, right? So this will be left, I'll be left with what? And I'm sending over the PNT as I'm sending this over, this term on the side, and then I'm dividing everything by h, right? So if I divide this by h, this is lambda plus mu. Just make sure that it's correct, right? Is this correct? Okay. Okay. No, all you have to do is just send this term here, expand this out, right? And take this term PNT on the left hand side. So this is where you get this, right? And then you divide across by each for the entire thing. Yeah. So that's how you end up with this equation here, right? So okay, so it's okay. So now we're going. If we have steady state, the change of PNT in the interval h will be zero. Okay. So that means that this first part that I'm saying here, this part here will go to 0. And what you'll be left with is this is 0 is equal to these 3 terms here. And I can rewrite this now as like this, right? So this is what I'm just rewriting it. So I'll have lambda Pn minus 1 plus mu Pn plus 1 is equal to lambda plus mu Pn. Right, so this is what I'm going to call equation 1. Now, the ideal thing to do is we need to get some expression with Pn. What exactly is Pn? But Pn here is written like a recurrence relation. So now we have to find some way to, get rid of this recurrence relationship. So one way that we could do that is that we could always start from the ground up and build, right? From P0, P1, P2, etc., and see if there's a pattern, and then replace what we need to replace. Right? Okay, so let's see. So let's consider P0 T plus H. That means that at time T plus H, we have 0 items in the queue. So that is the same as having 1 item in the queue. But then you have you have no service. You have 1 service. And what? No arrivals, right? Plus you have 0 in the queue, and then you have no arrivals and no service. Now you could tell me why I didn't have like P2T. Yeah, you could only have one item taking place, right? In an interval of size h, right? So we can't have P2T inside here. So what we have so far is just this, right? And we're going to repeat the process again, what we did before. So what we're going to do is we're just going to write down PO T plus H is equal to P1 T. Now, that means P1T means what? It means that you have 1 item at time T, but then you must have what? 1 service and what? No arrivals. So 1 service is mu H, and no arrivals is 1 minus lambda H. Right? So that's that. And we're going down again. I should say plus POT, the probability that you have no events at time T, times the probability of no arrivals and no service, right? So no arrivals and no service. Now, who could tell me was now I have 1 minus lambda H, and somebody said that this should be 1 minus mu H. Now, is this so? What is right or what is wrong in this last statement here? Right. Okay, this one.
Yeah.
So I'm asking, okay, so I'm saying that the probability that I have 0 items at time or 0 individuals at time t plus h is equal to the probability that you have 1 person at time t, right? And then that person has to leave, right, with this probability, and then you must have no arrival. So this one is okay. What I'm saying is this now. Now, suppose now I have 0 persons at time t. In that small interval, what must happen to have 0 at time t plus h? Yeah, none. Well, what? Yeah, I must have no arrivals, so nobody should come in. So this part is okay, but nobody could leave because I have nobody in the system, right? So this part here is 1, right? So this part here is 1, right? Because there's nobody in the system, right? Now what we're going to do, just going to repeat the process that we had before, and we're just going to write it as P0 t plus h minus P0 t all over h, right? And this is equal to P1 t mu minus P naught t lambda, right? Again, what happens here? This part here goes to 0, right? So then I'll have 0 here equal to this part on the right hand side, right? So now things are looking up. So this will be mu P1 is lambda P0. So that means that P1 is equal to lambda over mu times P0. Huh? What do you take down wrong? Wait, I'll just reverse. I'll just go back. Which time? You good? Fine. Okay, so this part here, because we're in steady state, this part here is 0, right? And then we'll have this being equal to 0. So I can make P1 the subject of the formula. So the probability in steady state that I'll have 1 item, right, in the queue would be equal to lambda plus, would be lambda multiplied by P0 over mu. Now, I could keep on using this process over and over again. So now this is for, I get that from here, right? From here, I get that. Well, which part? Which one?
Yeah. Oh, that means.
Okay, so we're good with this? All right. Okay, so the process is this now. We have this expression here. Let's call this expression, let's call this maybe 2. And we want to get, so the idea is this. So what we want now is this. Is to get some probabilities, P like P2, P3, etc. Well, what we really need is some general Pn. So this is what we are after, right? What is the what will Pn look like, right? Now, to solve that problem, all you need to do is look at this expression here, 1, right? And put n is equal to 1 inside this expression. So you'll get an expression with P1 in it. This will be P2, and this will be P0. So you'll have P0 in it, you'll have P2 in it, you'll have P1 in it. But we already found an expression for P1 in terms of P0. And now what we're going to do is find an expression for P2 in terms of P0, etc. Right? So that's what we're going to do. So we substitute. Yeah. Any person's what?
That's at the same time. It's
Yeah,
possible.
yeah, which is possible. No, it's not possible. Why? Yeah, within the H, because we are assuming that H is a small interval, and we are assuming that there could only be one event in a small interval. Right? So we can't have two events. So we cannot have an arrival and a departure at the same time. Right? So when we look at 1 that you wrote down just now, and you put n equal to 1, we get this expression here. Right? And I could, remove this yes, right? And after that, what I can do is I could replace. I already found that P1 is equal to lambda over mu P0. And if you make P2 the subject of the formula, you'll get this. And this would be right. So you have to simplify it a little bit, right? And you could work out these things. Maybe I should not have jumped the gun to P0 here as yet. Maybe I should have left it in terms of lambda P1 plus mu. So we have this expression across here. So what you will notice is this. Okay, you all have this? Which one? This? Okay. Okay, so you're substituting n equal to 1 inside the general expression that we found before with the Pn, and the Pn minus 1 and the Pn plus 1. Right? So this is what we're doing. And when we put n equal to 1 inside that expression, yeah, this is what we get here. Right? Yeah, and the goal is, so the goal is just to make P2 an expression in terms of P1, and then we know we could write P1 in terms of P0. So that's the idea. It's just to replace it. Each term to replace each probability with P0 inside it and some constant. So that's the goal. So in general, what we should have. So in general, you should end up with this. That lambda over mu to the n time P0 is equal to Pn. Right, so this is a general term that we should end up with. So what we're going to do now is this. We're going to take this lambda over mu and we're going to call that rho, right? Up here? Yeah, so okay, so watch across here, I have P1 is equal to lambda over mu times P0.
Oh,
Yeah, so I could use that inside it and simplify it. So, okay, so what we're going to do now is we're going to define rho to be lambda over mu. Right, so that's what we're going to do. We're going to define rho to be lambda over mu. And so P0 is rho times P1, sorry, is rho times P0. P2 is rho squared times P0. Yeah, this is rho and this is P, right? I'll try to, which one looking like a P? This? Oh, no, there's a, when you see the turn like that, whatever, that's a rho, right? So from the time you see like a little turn, right? I agree with Mike. Yeah. So Pn. So we'll end up with this. Right. So this is what we call an intermediate step, right? So what we found, we started off with lambda mu and the number of servers being 1, and we end up with some general steady state probability Pn is given by this nice function here. What we want to do now is we want to find out some other, maybe some other items about this function across here. One of the issues here is that we still don't know. We still don't know P0, right? So we know, and all we know is that we know that it is some probability, but we don't know the exact number. What exactly is it, right? So from this, since we know it's a steady state distribution, we know that the sum of all the probabilities would be equal to 1, right? So So we apply the steady state criteria where we have the sum of the pi's is equal to 1 from I is equal to 0 to infinity. Right? So that means P0 plus P1 plus P2 plus is equal to 1. Right? And I'm going to replace all those, the P1 and the P2 with P0. So this is P0 plus rho P1 plus rho squared P2. This is rho, sorry. Plus is equal to 1, like this. I could factor out P0. And then things will look a little bit maybe you'll see that this first part now is the sum. Yeah, is the sum of an infinite series, right? So we could just write down the sum of that, right? So the sum of that will be P0 is A over 1 minus R, right? We could write that because we took rho, which is lambda over mu, to be less than 1, right? So we could write down that. So this means that P0 is equal to what? Is equal to 1 minus rho. So this means that in general, our Pn, which is what? 1 rho to the n times P0 is equal to rho to the n. This is a rho. Times 1 minus rho. Right? Yeah. Good with the rest? Right, so we're just substituting this here. Over here, right? And that's how we end up with this. So now we have the probability or the steady state probabilities, right? At n, Pn is given by 1 minus rho by rho to the n. So that means that we know everything about the distribution now, because we could find any probability and we could find all these fancy terms that we spoke about. So the first term that we spoke about is that we said that when we arrived at this point here, this was like the intermediate step, right? And then we're going to use this step now. So we have completed the intermediate step. Now we will find LS, right? So LS is the expected length of the system, right? So this is the L. So recall LS is the expected expected length of the system. Right. So LS is equal to, well, how do you get an expectation? Right. So the question is how to get an expectation. It's something like this, right? Is a table like this that you normally work out. And these probabilities that we have here, the probabilities are what we are calling a P0, P1, P2, etc. All right. And what is N? Well, N is the number of persons in the system. The number of persons in the system at time 0 is 0. At time 1 is 1. You could have 2 persons in the system, 3 persons in the system, etc. Right? So in order to get this expectation here, what we have to do is we have to multiply. We'll normally do this. We'll multiply N by the probabilities and we'll sum it, right? Or go to infinity. So let me just erase this. So now we know what we're going to do. It appears to be, yeah, the row into 1 minus row. If you think about row as a success and N is a number of trials, yeah, you could think about this as a geometric, yeah. So this here is the sum of j is equal to 0 to infinity of j times pj. Right? So this is how you get the expected value for the number of elements in the system. Remember, the system can start with 0 and you could go all the way up to infinity, right? So what am I going to do now? I'm going to replace that that pj with the probabilities that we know, right? So this is what? J times rho j times P0. Right? So Pj is rho, this is rho j times P0. From this is j is equal to, let's say, j is equal to 1 to infinity. Now j is equal to 0 will disappear, right? Because when you have 0 here, this disappears. It's 0. So we can start the series at 1. So I could take off a P0. I could take off rho. And then I'll have j is equal to 1. Is it AC? Okay. So j is equal to 1 to infinity, right? So j is equal to 1 to infinity of let's see, if I take out a rho, this would be j times rho j minus 1, right? So I'll have it like this. Right, so now this, what I could do is I notice that this part here is the differential of rho to the j, right? Like that, right? If I differentiate this with respect to rho, this j will come here, and this will be j minus 1, right? And I could switch these things. I could switch this differentiation and this and the summation sign. So I'm going to do that now. So this is P0 by rho by D, the rho of the sum of rho to the j is equal to 1 to infinity, right? Maybe I should just put this. So this is what? This is P0 by rho. This would be D rho. This sum here would be what? This would be what? The differential of sum would be what? Rho plus what? Rho squared plus rho cubed plus like that, right? Let me just put this few dots there. This is P0 rho, and if I differentiate these terms here, now I'll get what?
L1 plus 2p.
Oh,
plus
so
3p squared.
yeah. And well, I think I made it right. So if I differentiate that, this would be the sum, right? Maybe I should not have done it like this and just if I move this across, move this here, this is the sum of j, that's 1 rho squared dot dot dot. Right. So okay. Right. There's a one that I did not take care of. Or did I take it off already?
Why is this?
Yeah.
I
So I have this j is equal to 1.
have L1.
Pepper j is equal to 0. This will be 1. The first term here will still be 0. Anything to power 0 is 1. I'm supposed to get. Am I missing out ones somewhere? P0 rho dt. This is supposed to be 1 plus rho squared plus rho cubed.
All right. So there is still taking back to the equals. Before you change any and then you pull out the differential.
I'll leave it at 0.
Yeah.
Yeah. Right. I could still put it at 0 here. Make sure. It says j rho to the j P0. This will still be 0. So the first term will disappear regardless. Right? And this one here is the differential of. So this is the differential. So this is the differential of rho j. Right? And then, okay, so then I'll have, so this is 0. So this is 1 plus. Right? That's 1 plus. Yeah. Yeah, that's correct. Yep. So let's see. So this would be d rho. Now what is this? This here is the sum of infinite series. First term is 1, and the second term is rho. And the common difference, sorry, is the geometric ratio, sorry, is rho. So and rho is less than 1, right? So we could express it like this, and then we could just differentiate it. So if I differentiate 1 over 1 minus rho, that's 1 minus rho squared with plus 1, right? Because, and yeah, it'll be a plus 1 because the minus and the minus will disappear. So I'll get a plus 1. This? From 0 to infinity. Okay, j is equal to 0 is 1. Rho to the power 0 is 1. Yeah, yeah. So I just expand out this thing here. Yeah. Okay, so this, okay, so you understand this part? So we're okay here. The next step is just to replace what we know P0 to be. Right? So P0, we had this as what? What did we write P0 as? It was 1 minus rho over 1 minus rho squared. So this here would be rho over 1 minus rho. Let's make sure that P0, what did we have P0 as? 1 minus rho alone? In previously, yeah. Just go back to P0. Yeah, it's 1 minus rho, right? Okay. So we replace P0 with 1 minus rho, and a 1 minus rho will cancel off here. So you'll get rho over 1 minus rho. So this here is the expected expected length of the system, right? So this is our LS, right? So if in an exam you're asked to prove something like this, the only term that you might have to prove is just this one here. It's just LS, because LQ is a function of LS. So LS, the expected length of the system, could be considered as the expected length of the queue, LQ, plus the expected number of people being served. So LS is the expected length of the system LQ is the expected length of the queue. Now, remember the difference between the system and the queue, right? The system, when we talk about the expected length of the system, we are including the person being served, right? When we talk about expected length of the queue, we are just talking about everybody else who is waiting, but not the person being served, right? So the expected length of the system would be the expected length of the queue plus the expected number of the persons being served. And the expected number of persons being served will simply be the arrival rate over the service rate, right? So this term here is simply lambda over mu. And there are two other terms that we need to work out here. We spoke about LS, LQ, then we spoke about what? WS, WQ. And WS is the waiting time in the system, and WQ is the waiting time in the queue before you actually reach up to the server, right? And we have little equations, Q equations, and they are given by LS is equal to lambda times WS. So the expected number of persons in the system is equal to lambda multiplied by the waiting time in the system. The expected waiting time. And there's another result, LQ, which is lambda times WQ. So these equations were derived by Little. Huh? Which one? Yeah, no problem. Watch it. So if this is your server here, right? And okay, there's one person here, right? So suppose this is you, right? And you have people join after you. Let's call Jim Jones. So Jim and Jones join after you. So in this case here, the system, when you talk about the system, is everybody, including the person in front of the server. So in this case, the length is 3 of the system that we are seeing here. So it's not a probability annex. So you go in front of a line in a grocery or something like that. There's one person at the cashier, and they have 10 people after that lineup. So the length of the length of the system is 11, 10 plus 1. But the queue length is you delete the person at the cashier, so whoever remains in the queue. So that's 10. Yeah. But we have to remember that these things here, we are treating these things here as random variables. So it's not like, so we are not assuming that we are assuming distributions, lambda rates and things like that. When you actually go and you take a snapshot, like a picture, what you see is an observation. And that observation doesn't have any distributions attached to it. It's just like a picture. You take a picture, that's it. That's the length of the queue. So it have no arrival rate and no exponential rate and all these things attached, right? So that's when you talk about system, is everybody, including the person at the cashier, right? When you talk about queue, queue is everybody except the person at the cashier. Oh, okay. Yeah. No, well, yeah, the expected number in the system. When it says system, like in physics and things like that, well, I think when they use that term, system is like everything. Right? The queue is, you could think about the queue as a subset of the system. So if you are asked, right? So I'm repeating this. If you are asked to prove something like this, so to derive the PN, right? The steady state probabilities, what you need to get, you need to go through the process. And if you are asked to prove these things, these four terms here, LS, let me get them. Where do I have them? LS, this is the first one, LS, LQ, WS, WQ. What you do is this, you prove LS. That's the first thing, you prove LS. And after you prove LS, LQ, to get LQ, the expected for LQ, you use this equation. You use this, right? And this will give you, if you make LQ the subject of the formula, you will get LQ. Yeah, because this part here is just lambda over mu. So you just send that on that side and that's it. It'll be LS minus lambda over mu, right? And if you are asked to get WS and WQ, you don't have to prove anything. Just apply Little's equations, right? And these are your two equations here that we have. LS is equal to lambda times WS and LQ is equal to lambda times WQ. And you know this LS, you know lambda, just make WS the subject of the formula. That's all. Right? So that's it. Okay, so let's try to, let's try a numerical one to see, how this really plays out in the real world. So we're still looking at a MM1Q, right? So let's see how we could, how this will play out. So let's take some numbers, because sometimes it's only when you use numbers, you might get a better grasp of what is going on. So an example, a numerical example. We're just going to, we are using, thinking about a MM1Q, the same MM1Q. And if you see MM1 by itself, just by itself, it means what we had before, MM1/infinity/infinity, right? So doesn't matter to us, right? So lambda is equal to 8 and the mu is equal to 9. So I'm saying 8 arrivals per hour and service time is 9 per hour, right? So in this case, rho is lambda over mu. This is how we define rho. This is 8 over 9, right? First things first, let's find P0, right? So P0, according to our definition, was that what we proved above is 1 minus rho, which is 1 minus 8 on 9, which is 1/9, which is 0.11, right? So what does this mean? So this is a probability that there are what? No persons in the system, right? So this is the probability that there are no persons in the system at steady state. So at steady state is where we have these nice assumptions. And think about steady state is also as a way for you to estimate these probabilities. If we don't have restrictions, we cannot estimate things. So because sometimes we have too many variables, so restrictions help us to be able to get these things. All right, so what is the probability if I say, okay, what does 1 minus rho mean? Right, so somebody says, okay, I know what P0 is, but what is 1 minus rho? That's the probability that they will always, that is, the system is not what? System, okay, P naught is 0.1, right? Oh, sorry, supposed to be P0. So if somebody, you write down it. What does 1 minus P0 mean? Yeah, you must have at least one person in the system. So that means the system is not what? Empty, right? All right. So that means so I'll put down, this is the probability that the system is not empty, right? Okay. All right, so let's go again and work out some more. Let's see. What's the probability that there is no Q? Or no persons in the system, exactly. The probability that there is no Q means that you could have one person at the server, or you have nobody at the server. Right? Huh? This is not normal. Okay, it's still working. So so this is what? This is P0 plus P1, right? So this is what? This is, we had this as what? 1 minus rho, and this was rho by P0, which is 1 minus rho, which is what? Which is 1 plus rho is the 1 minus rho. Yeah, which is 1 minus rho squared. Okay, well, is this right? So if you work it out, you get something. So you could ask the front question. What's the probability that there are 10 persons in the system? That's just what? P what? Yeah, P10, right? Which is rho to the 10 by 1 minus rho, right? This is how we define it. Right. Okay, so we know, so we can handle probabilities, right? What's the probability that 2 or more persons are in the system? Yeah. So that's 1 minus P0 plus P1, right? This is about 0.7902. You could check it out. Let's see. So let's work out the expected LS now, the expected length of the find LS. LS is the expected length or the expected number of persons in the system, LS, right? And we found that just now to be what? LS, we worked it out to be, I think, rho over 1 minus rho, right? Right? So this is simply 8 over 9 over 1 minus 8 over 9, which is 8. So on average, right, what you would expect, you will expect to see 8 persons in the system, right? That doesn't mean that every time you go there, you will see 8. right? The number will vary, right? But over a long period of time, what you'll expect to see is 8 persons in the system. Let's work out LQ. Now we said that LQ was equal to LS minus the rate, lambda over mu, right? Which is rho, right? So remember that rho is lambda over mu, right? So this is 8 minus 8 over 9, which is approximately, say, 7.1. Now that makes sense, right? That makes sense because you expect more persons in the system and less persons in the queue over, over a long period of time. Well, it depends. It depends on which one? Four, right? It's okay. All right. Five. Okay.
Like in this case,
What?
I see.
Which one? Yeah, that's probabilities, right? So that's P0 and plus P1, yeah. You got it? All right. So, okay, so the other one that we needed to work out was these W's, right? The WS and the WQ, the waiting time. So the waiting time or the expected waiting time that you will spend in the system is LS over lambda. So this is from Little's equation. So this 8 over 8, which is 1. So you expect to spend 1 hour, right? And WQ is LQ over lambda, the arrival rate. So it's just 7.11 over 8, which is about 53 minutes. So this is 7 and 1/9 divided by 8 by 60 minutes, right? 1 hour. So it's about 53 minutes. Right? Okay, so we'll stop here for today, right? And we'll continue on Wednesday. I have all your scripts, so I will return them on Wednesday. The only thing I don't have is your assignment. What? Your assignment 4. Leave it. Okay.